Hey physicists, if you're having a little problem getting started on the racetrack optimization project, here are some ideas. Hey, first notice here that you do have your selection of a couple of different chassis. Depending on their mass, they cost more money. Remember, less mass means that for the same force you have greater acceleration. Hey, the motor. We're not worried about traditional horsepower. We're looking at the force each of these puts out. We're assuming that it puts out that amount of force all the way from 0 miles per hour or meters per second up to the maximum speed. Once it gets to a maximum speed, it just stays at that maximum speed. Downforce package, as mentioned here, our frictional force we know is a function both of the normal force and of the coefficient of friction between our two surfaces. Downforce is an addition to the weight for normal force. The nice thing about downforce is that if we go up or down a hill, that downforce is always acting at 90 degrees to the hill. We don't have to worry about, let's say with gravity, if we're going up or down a hill, that only a portion of that forces into the hill. And finally, where the rubber meets the road, literally, tires. And so we're looking at different coefficients of friction. All right. Remember, it is friction that helps you speed up. It's friction that helps you stop. It's friction that gets you around corners as well. Hey, and maybe an approach to the problem. I'll leave it up to you how you exactly do it, but just some ideas. Hey, and I have a note here is that we always have constant speeds and turns, and that's going to be a function of the centripetal acceleration that your car can produce going through that turn. Larger turns will have larger velocities, tighter turns will have lower velocities. Of course, it'll depend on the maximum frictional force that your car can generate, as far as that becomes the centripetal force. See the note here, we're assuming that we're at constant velocity. So really the racetrack, as we go around here, I like to think of it as being, hey, is a series of turns that we figure out what our constant velocity is through each of these turns, and those are connected by straightaways. Hey, I've got kind of a cutaway if you want to think of that. It's one straightaway and one turn. All right, but it illustrates what we're looking for. Hey, so on the turn, you can pretty well figure out the centripetal acceleration if you know the mass and the coefficient of friction. We're assuming that all of the turns are on a horizontal, so the only centripetal force is going to be the frictional force. How about in a straight line? Hey, so when I come out of a turn, my initial velocity is the velocity I exit out of that turn. Through the entire turn, I'm going at a constant speed. So that you can see where that, if we go around this clockwise, that as I leave the turn, that becomes my initial velocity for a for a straightaway. Straightaway is made of 3 sections. We have a section that we speed up. We have a section that we're maintaining our maximum constant velocity, and then a section that we're slowing down before we get to the next turn. At the end of this braking section, you see our final velocity becomes the speed that we go through this turn, which is the next turn's initial velocity. As it is turns that will indicate our initial and final speeds for straightaways, good that we go through and we calculate the speed for each of the turns. Now that'll depend, of course, on the selection of components that you have for your car. In addition to knowing what the velocity we have to go through that turn, we also need to know what the time going through the turn, because we need a total lap time. Okay, so let's take a look what's happening here. Some of these values, many of the values are calculated, other ones are given to us. We made a selection of a 1,000 kilogram mass car, so we know that the weight of the car is 10,000. If I look in here, I can see up in the formula that to get the weight, all I've done is taken the mass and multiplied it by 10 newtons per kilogram. Our downforce is bought, so that's just an assigned value. Now I'm going to go over here to the total normal force, which will be the sum of the weight plus the downforce. I don't have to calculate that each time. I've already put that formula in the cell. So let's say, I selected a car that was a little bit lighter, and I put in the value, oops, 900 kilograms. Note how all the weight, there it goes, the weight and the normal force all dropped. Frictional force also dropped. And what does it look like? Our maximum centripetal braking? Yes, that looks like that may have dropped as well. All right, so I'm going to go return this back to 1,000. Let's see how these change. Yep, they've all gone back. Hey, so take a look at this. Normal force is the sum of our down force plus our weight. If we're on a hill, watch out. Coefficient of friction is a given amount because our frictional force, we can see here, it says E3 times F3. E3 is our normal force. F3 is our coefficient of friction. If I want to check the performance of different tires, I can put a different value in for my coefficient of friction. You know, this becomes kind of an important one, our maximum acceleration for centripetal or braking. Let's just talk about our centripetal acceleration. Hey, remember that our centripetal acceleration is our velocity squared over mass, but this is also our net force. Okay, so our maximum frictional force becomes the force that causes centripetal acceleration. And I'll let you figure out those things. Our turn radius is given to us, and then we figure out what I had a note here, the velocity squared. Velocity squared comes out of that equation fairly easily because we know acceleration is equal to the velocity squared over r, or another way of saying acceleration times r is equal to velocity squared. So I just have it as a checkpoint. We take the square root of that number to get our turn speed. Hey, because we're talking about a speed and we're on a racetrack, we don't have to worry about the plus or minus when we take a square root. Hey, we do have to figure out what our time through the entire lap is. So here's a time for one turn. I need to know how many degrees in the turn. At least I listed that. That'll give me the distance, and I know my turn speed. You can see here that I've got a formula here that tells me the length of my turn. Okay, I might effectively have a quarter of a circle, and I divide that by my speed going through there. That'll tell me my time going through the turn. This happened to be 3 different examples, but really it's the same equation. Once I figured out for one line, I just copied it down. What kind of changes did I make? One was a smaller turn radius. I ended up having a quicker time, which makes sense. It's not as far. And then the other one is a larger turn radius at a, let's see, what are we doing? Obviously, I have a higher speed, and I end up having a longer turn time because it's 180 degrees, so it's a half circle. As I mentioned before, the straightaway is composed of 3 sections. Our acceleration section, speeding up, you'll see this tab down here. I've got that identified. I also have a constant velocity and then a braking section. All right. Hey, so let's take a look at this configuration. I went with the cheap model, some notes to myself. Again, the mass, weight, downforce, total normal force of the calculations as before, as is with our coefficient of friction. And so we end up having a maximum frictional force. Now, just kind of a bit of a heads up here, that when we look at our maximum acceleration for centripetal acceleration or for braking, we can use all 4 tires. But unfortunately, we only have 2 tires available to us for accelerating. So you'll see that our maximum rear wheel traction, this value here, okay, looks at what our maximum frictional force, and how do I end up having that? G3. So I follow this column down, I see G3 is my frictional force, but my traction force for accelerating is only half of that value. We can see it's calculated up here. G3 times 0.5 gives me my maximum rear wheel traction. Hey, now I have to look at something. That's the maximum rear wheel traction, and I have an engine force that's 6,000 newtons. Can I support that? If I had a very powerful engine and I had slippery tires, it wouldn't work well. I would be limited by the maximum traction. So in this case, I said, what's my maximum engine force? What's my maximum wheel traction? I did a logic operation. Let's see if we got that. Yeah, you can see here in K3, I have something that says minimum I3 or J3. I'm looking at either of these two, and then I have to decide, hey, so the car will only either have the minimum of engine force or the minimum of the wheel traction. Okay. Figure out an acceleration. We know enough about that. It's a force divided by mass. And I can from that figure out what my, let's see, figure out my acceleration, what my maximum speed is going to be defined by the car. I can figure out a distance and the time it takes to travel that. Okay, my turn speed, or the end or the initial velocity, is listed here. So really it's saying with this acceleration, what's the distance and what is the time to go from 22.4 meters per second to 105 meters per second. And connecting the accelerating section and the braking section is just a constant velocity section. So let's say for the car I've got here, it would just be a matter of how far and how long does it take to travel a section of track at 105 meters per second. Hey, the next interesting one is under braking. All right, again, we have our normal force and coefficient of friction to figure out what our frictional force is. Hey, all of that frictional force is available to the car during braking because all four wheels are used to slow it down. So maybe it's a little bit simpler calculation. We just look at our maximum acceleration, our centripetal acceleration, or braking because all four wheels are available there. I've got a maximum speed. I'm going along the straightaway at my maximum speed. Hey, my next turn I have to be down at 22.4 meters per second. Hey, using our favorite kinematic equation, we could say that this is our initial velocity. Here's our final velocity. We could probably figure out what that distance is, or delta x, given this acceleration. Once we have those values, we can figure out how long it takes for the car to travel the distance while slowing down. So perhaps that helps you see at least how I approach this problem, that each of my straightaways is composed of three sections. There's the accelerating section, there's the constant velocity straight section, and then there's the braking section. What do we have to get through? We have to get through each of the turns, given the radius and length of that turn. So we're really just connecting one turn to the next through a piece of track that we accelerate, travel at constant velocity, and then start braking. Our last expert TA problem had a problem with an elevator going up an elevator shaft. It accelerated constant velocity and started slowing down. Really, our three calculation for the straightaway is the same as as you did in that part. The only challenge is that you're given the distance in the racetrack, whereas in expert TA you were given the time for each of those sections. All right, hey, so work diligently and make good progress.